So let's start this lecture 6. So what's the main result that we get last time? What did we do last time? The main result. No, somebody wants to say something? Oh, okay. So we prove that if f is continuous, the initial value problem has a solution, right? Okay, this is called the Cauchy-Peano-Arzela theorem. All right. So next, so the Cauchy-Peano-Arzela theorem doesn't deal with uniqueness of the solutions. To have uniqueness, we have to add some assumptions, and this is the purpose of today, right? This is the main purpose of today. So to introduce, the theoretical result is called the Cauchy-Lipschitz theorem. So to start with that, I suggest the following exercise. And so, yeah, let's try to find the solutions of this equation, and then we talk about that. So you can try to solve this exercise that you can see now. So next, we are going to deal with the Cauchy-Lipschitz theorem. So first of all, we have to remind the definition of what is to be locally Lipschitz for a function. Everybody knows that? So you can try to write it down. Okay. And so here's the definition for those of you who are on the call. All right. And then so I'm going to write it on the board in a few minutes, but it's a good exercise for you to try to remind what it is. And then okay, so this is the theorem of Cauchy-Lipschitz. If we assume that f is locally Lipschitz, then the phenomenon which occurred cannot happen. All right. If f is locally Lipschitz, there's one unique solution. So we can prove that there exists a time t, and the solution is unique. You cannot have two solutions that emerge from one value. So what's next? So next, we want to prove that the sequence provided by the Euler method converges to the solution. But before to do that, we are going to prove this lemma that you can see. Yeah, and so it's called the discrete granule lemma. So I suggest you to try to think about how to prove this theorem. So I let you work on that a few minutes. So next, we want to prove that the sequence provided by the Euler method is going to converge towards the solution. Okay, but now, if you replace, so you can replace 1 and 2. So now let's assume that here I have UP and UQ, where UP and UQ are provided by the Euler method. All right, so, and when P and Q becomes large, epsilon P and epsilon Q becomes as small as you want. So this inequality means what? Means that the sequence provided by the Euler method is a Cauchy sequence and a uniform Cauchy sequence. And it remains in the compact. We saw that previously. So, and this compact is a complete set. So you have a Cauchy sequence in a complete set, it converges. And it converges uniformly, and we saw that in this case, the limit is solution of my ODE. So that's the proof. So we prove this theorem. If we assume that f is locally Lipschitz, then the sequence provided by the Euler method converges uniformly towards the solution of the initial value problem. So classically, you have another proof which is based on the fixed point theorem. So basically, you write, you start with the integral equation, and we start with an initial function, and then you apply it. So this gives you an iteration, and if t is small enough, then this map K will be contracting. So this is just a global idea. I can provide references where you can look at it. It's very classic, right? You can look at the book of Tesk or Perco, which are in the references, and it's in there. It's also in the Demailly in French. Okay, after that, so we proved that we proved the Koshil theorem. So the Koshil theorem, the proof we gave, works with some t, but you can always extend the solution that we constructed to be a maximal solution, right? So we will prove that in a few minutes. And finally, this result. So now we assume that f is defined on R times R to the m, and that f is Lipschitz, is globally Lipschitz. Then your unique solution is defined on R, so it's a global solution. All right. And to end this chapter, I can give you some homework. You look at what is the granule lemma, and you try to prove it and understand the proof. So the granule lemma is a general result, which proof is very close from what we did today. So you can do it as a homework. You go, you look for it, and you try to prove it. All right. So this ends the chapter 2. So next time we will start the chapter 3.